record on this computer. There we go. So yes, the integral test really outlines that there is a strong connection between what we're doing here with series, when we're adding up lots and lots of things, along with what we did in chapter 7, when we added up lots and lots of things, right? And the big thing in chapter 7 is that we had continuous functions and stuff like this, right? And we talked about an integral, but this is adding up the area under these sorts of functions. And essentially, this is really what we're doing when we're taking a series, when we're summing up items on the list, right? If you have those items on the list, and if we plot them, right, and you can plot them, they're at different heights. So maybe, of course, the bigger ones appear at larger y values, they're higher up, and the smaller ones, are lower y values, they appear farther down, sort of deal. But still, you're adding lots of things up, and in particular, right, you can think about if you make these rectangles of width 1, well, then the area of this rectangle is given by the height times the width, which is, well, exactly those terms, right? And so there's a strong connection between the area under a function, a continuous function f of x, aka an integral, along with these series, right, is when we add up these items on a list. And you saw in the video, right, kind of sometimes you're a little bit more, sometimes you're a little bit less, right? It's not that they're going to sum to the exact same number, but so long as some conditions are met, if one goes to a finite number, so will the other. And if one goes to an infinite number, infinity, right, then so will the other, right? And so there's a strong connection here, right, between adding up or integrating a continuous function here and a series, right? Adding up these items on a list. And the main thing that we need in order for this to be true is 3 things. We need that our function is continuous, so we're not trying to do anything over, some discontinuity here. We need that it stays positive, and we need that it's a decreasing function. And if those 3 things hold, then we have this strong connection. And instead of thinking about the series, which are kind of quite mysterious to us still, we can instead think of an integral, and those we're much stronger in from our chapter 7 days, right? We know how to integrate lots of functions, and we can say whether they converge or diverge thanks to our improper integral information, chapter 7.8. So, okay, that's the integral test. This is the basis for a lot of stuff. You'll see as we continue on in chapter 7 that this test right here is quite tedious, that there are a lot of hypotheses here. This continuous, positive, decreasing, checking those things to make sure that it actually holds takes time, right? And so we will go through it and show you kind of what's expected of you and everything to check whether those things are true. And then once we have that, we can come up with a conclusion here. But those will take time. And you'll see kind of as we progress into 11.4, 11.5, 11.6, stuff like that, they have fewer hypotheses, which is nice. And so you can apply those tests a little bit faster. And so this one is kind of a bit of a stepping stone to some extent. There are some problems, mind you, that this can solve and that none of the other tests that we'll learn can solve. So it's not like you can forget about this one by any means. So it's not, like completely a stepping stone that we eventually get to, just throw away. But we will prefer to do some of those later tests more than this one if possible. Okay, so we have that, and then I showcase the strategy for showing if some of these series converge or diverge. We get something called the p-series test. So this is a nice kind of shortcut. If you have a series that looks like 1 over n to the p, then by using this integral test, we can come up with, does this thing converge or diverge? And we can see that if p is greater than 1, we know that it'll converge. If p is less than or equal to 1, it'll turn out to diverge. And you can see that this is actually relating quite closely what we did last time with a harmonic series, right? The harmonic series, when p is equal to 1 here, that this actually diverges. We showed that last time. And so, yeah, the rest of the section was kind of showcasing some examples. I also gave a bit of a shortcut here, right, showing that something decreases, right? So in order to apply the integral test, we need continuous, positive, decreasing. And the most painful, most tedious one on that list is to check if it's decreasing. And so formally, in order to check if something's decreasing, the best way that we know how is with the derivative, right? We take the derivative, we see that it's less than 0, and that's great. However, right, there are some kind of shortcuts. You can make some nice theorem like this, which by the way, these aren't in the book. But it does make these problems go considerably faster, right? And that's just making up some quick theorems as far as if you have some pieces and you combine them in some interesting way, how do you know if the result is increasing or decreasing? So in particular, right, if you have two increasing functions and you add them together, it stays increasing, right? If you have an increasing function and you take the reciprocal of it, right, you're getting larger and larger values, but now you're putting them in the denominator, that means it's going to be decreasing, right? You're going to get closer and closer to 0 here. Multiplying by a constant doesn't really change if it's increasing, so long as that constant's positive. Of course, if you multiply by a negative number, well, then you're going to have a decreasing situation. So this is a big list of theorems as far as the increasing and decreasing, and we'll be using a few of those throughout today's class as well. But yeah, so these kind of speed some things up for us a little bit. All right, so that's the videos in a nutshell. I'd like to get to some problems here. Let's see, maybe I can take one or two hands. So Jonathan, I saw your hand up here. If you have a question for us, the floor is yours. Hello?
Oh, I did that by mistake, so I don't have a question.
All right, yeah, no problem. All right, then Joe, goes to you.
Professor, I was just wondering, when I was doing the web work last night about the nth term test, when does the nth term test not apply?
The nth term test does not apply if that limit actually approaches 0, right? If the limit approaches 0, then you can't say whether it converges or diverges. If it approaches anything but 0, then we can say for certain that it diverges.
Okay, I had the theorem confused that if it reaches 0, then it converges, but I guess I'm wrong. It's just inconclusive.
Exactly. It's just inconclusive. Okay. Yep, exactly.
Okay, thank you.
Yeah, of course. Yuan, any good questions in the Q&A that we should talk about?
Yeah, before that, I want to ask a question. Is about from my office owner. He's asking, will they study the monotone test?
The monotone test?
Yeah, it's the alternating, for the alternating series. It's an increasing function.
For an increasing function?
Like 1 minus 1/2 plus 1/3 minus.
Oh,
yeah.
Yeah. We will get to that in 11.5. We have an entire section dedicated to the alternating series test. So yes, okay. Maybe this is just like by a different name or something, but yeah, we have something called the alternating series test, and we'll be able to say with quite, a lot of confidence that the alternating harmonic series will end up converging. But we haven't gotten there yet. Okay.
Another good question is, how does Riemann sum fit into this test?
Well, again, Riemann sums are, the same thing. Well, limits of Riemann sums are going to be, of course, the same thing as the area under some, nice continuous function like we have here. So these are certainly related with the integral. Now in Calculus 1, when we were doing Riemann sums, we never took, our bounds to be to infinity. So that kind of creates a little bit more of a headache here. But yeah, in the background, we are using some Riemann sums again in order to evaluate out this definite integral. And so, yeah, they're out there. And this you can think of as similar to a Riemann sum, but over a rectangle with a specific width, a rectangle of width 1, rather than letting the rectangular width get smaller and smaller and smaller. Good. Any other question?
No. Someone's asking how many pies do you know? How many digits of pi do you know?
I don't know. Too many. I think it was over 100, maybe 120 or so at one point. So it was substantial.
You remember all this? Or?
Yeah. Yeah.
Okay. That's impressive.
All right. So with that, why don't we go ahead and start talking about the integral test, some new problems here. Determine if the following series converge or diverge. Notice that we're throughout all of this today, you will never say, if it converges, what does it actually converge to? This is in general a very difficult question to answer. And actually we'll be talking about this a little bit more before class on Friday. So if you come a few minutes early to class, we'll be talking about the Basel problem. That's going to be my bonus math. But this one is a little bit related to, what we're talking about here. So if you come maybe 5-10 minutes early, we'll be talking about the Basel problem, a very interesting historical problem of trying to sum up the reciprocal of the squares. So, okay. Again, when we ask these sorts of questions, we're just going to ask, do they converge or diverge? So this one right here, this will follow directly from the P-series test. So this will converge by the P-series test. So remember, the P-series requires it to be in the form 1 over n to the p, summing up from n equals 1 to infinity, right? And the P-series test says, if your p-value is greater than 1, that it will converge. So in this case, if I wanted to justify this, right, I would say that p is equal to 5, which is greater than 1, right? So that's why I know that this is going to converge. Now, of course, if you don't want to remember the P-series test, which it's quite useful and it's not, too long or anything like this, you don't have to. You could also solve this with the integral test. But again, if you use the integral test, there are 3 hypotheses that you have to check. Is it positive? Is it decreasing, right? And is it continuous, right? So you need to check those 3 things. But notice with a P-series test, when you have it in this very specific form, right? The P-series test doesn't have these hypotheses because it knows in this form right here, you don't have to worry about those things, that it's going to be positive, that's going to be decreasing, that it's going to be continuous. And so, yes, we can say this quite quickly. Now, of course, you can make this a little bit more complicated. So here's a situation like this, where formally what I would like to do, again, we're still going to be using the P-series test on this. But what I would do in this case is that I'd go ahead and do a couple of rewrites. So I would, for instance, instead of the square root of 3n, I would make this the square root of 3 times the square root of n. And then remember, when you have constants, in 11.2, we talked about one of the things that you can do is that you can factor out constants, right? So 5 and division by root 3, those are constants. They don't have any n's in them. So you can take those out. And so then what I'm left with is, well, there would be a 1 in the numerator. And remember, the square root is the same thing as the 1/2 power. So with the 1/2 power here, now we have it exactly in the form that we need in order to talk about P-series, right? And so this right here is a nice P-series. So we know that this will diverge since P is equal to 1/2, which is less than or equal to 1 by the P-series. And again, you could use the integral test on this here as well. And now, of course, if you have something that's going to infinity and you multiply it by a constant, remember, this is not going to change whether it diverges or not. This is a small theorem that I gave you guys in 11.2 in the in-class notes, right? That if you have a series that is divergent and you multiply it by a constant, so long as that constant's not 0, it's still, right, you're not going to get off infinity here. It's still going to diverge. And so that's why I'm certain that even with extra constants out in front and whatnot, it's not going to change that this is still going to diverge towards infinity. So again, these sorts of questions, we talked a little bit about this before class, right? It's right, converge, diverge. That's what we're looking for. And so these make excellent true-false style questions. They'll also make, multiple choice, nice multiple choice style questions as well, because you can just ask, you can combine it. It converges by the nth term test. It diverges by the nth term test. It converges by the geometric series test. It diverges by the geometric series test. It converges by the integral test, right? And so you just have to choose which one is accurate. And so they make for pretty straightforward true, false, or multiple choice style questions. All right. So 2 relatively nice ones off the bat here. Of course, we'll be dealing with more complicated things moving on. But yeah, any questions here before we start doing more problems? I guess, Ian, you have your hand raised. Why don't we go ahead and call on you right quick?
Oh, I just wanted to ask, on Friday, that's like the one day I'm not able to make it to class. If like, will you be able to record like where that class starts on Friday from the slideshow that you'll have?
Yeah, I'd be happy to record that. Sure.
Okay, thank you.
Yeah, of course. Yuan, please remind me to
Sorry, what's that again?
record the bonus math that I'm going to be talking about before Friday's
yeah.
class, especially because this
Okay.
one's a little bit more related to our actual class topics.
Mm-hmm.
All right, Andrew, what question do you have for us?
Hi, so for the P-series test, it works from 1 to infinity, but is there any way we could utilize the P-series test if we have, say, like 0 to infinity or 2? Could we like manipulate it in some way like we do for the stuff we learned on 11.2?
Absolutely. And that's just because, right, again, the only question is, does it converge or does it diverge? And so notice when I gave you this theorem that I remember the chat was kind of blowing up last time. Folks really like this for whatever reason, right? So long as you don't do something silly, you can change that lower bound and it will not change, right, if it converges or diverges, right? So that's the if and only if here, right? If one converges, the other one will, and you can change it from, you know, a 1 to a 3 or a 1 to a 10 or something like this. And that's not going to get you off infinity or not.
Okay, so that's the same, like a sub n would be essentially like 1 over n to the p in this case, and so it'll still work.
A sub n is just meant to represent any old function, any old list of numbers that relies on n.
Got it. Okay, thank you.
Yeah, no problem. All right, and let's go ahead and start doing another page here, and then we can call on more folks. Or actually, we should one maybe to the Q&A. Any Q&A questions that we should talk about?
Someone is asking the difference between the geometric series test and P-series test.
Excellent. So for the geometric series test, and I don't know what I should write this in. Maybe not blue because it's, I'll do purple here. So the geometric series test only works when you have a geometric series, right? So that means that you need a constant times r to the n. And notice that your n, this variable, this thing that's changing, is in the exponent slot, right? And so, you know, first is r to the first power, well, r to the 0th power, then r to the first power, then r squared, so on and so forth, right? So that's where your variable is. So an example of this would be kind of like 1/2 raised to the nth power. This would be kind of a mini example. Now, the nth term test, the P-series test that we're talking about here, this has the form 1 over n to the p. So an example of this would be 1 over n squared, right? So you can see that your variable, the n, right here is in the base of your function here, this 1 over n squared, while again, the n was here in the exponent slot. So that's going to be one of the major differences, that a clear identifier as far as when can it be geometric series test versus when can it be P-series. Excellent. All right, so the next bit, I have a relatively simple one here, but I just want to show you how fragile the P-series test is. So this right here, technically, we can't use the P-series test for. Now, there are very clever ways that maybe you could try to reindex this and all that sort of stuff, and kind of recover it in this case because it's so simple. But what I wanted to say here and why I brought up this problem is just that the P-series test only works when you have exactly this form, 1 over n to the p. Once you start adding things, once you start subtracting things, right? We saw that with multiplication that was okay, that we could kind of take out those constants out in front of the summation. But with the addition and subtraction, right, there's really no way to take those out. And so once you start having summing or subtracting or whatever, right, technically you can't use P-series with this as it sits. And so in that case, right, all we have right now, and we could kind of go through the list, and it's not a bad idea to always kind of go through this list. If you got this on the exam, right, when you have the whole chapter 11 material at your disposal, right? Maybe first you think about geometric series test, right? And you say geometric series test, well, it's not a geometric series, so this doesn't apply, right? For it to be a geometric series, we would need to have that n in the exponent slot. Then you could think about the nth term test for divergence. So nth term test. And if you took the limit of just the items on the list, 1 over n plus 1, this goes to 0. So remember, the nth term test is inconclusive if it goes to 0. Maybe it converges, maybe it diverges, we don't know. But the big thing is that the nth term test can't be used for this. So, okay, now we go down our list. We thought about p-series. We can't really use p-series on this. And so the next thing is the integral test. And the integral test, it turns out, we can use in order to solve this. So when we think about the integral test, right, we think about this corresponding function, this 1 over x plus 1, that we would like to compare it to. And hopefully, if we can make this strong connection, then we can look at the integral from 2 to infinity of this function here. And if this converges, we'll know the original converges. And if this diverges, we'll know the original diverges. But again, we need to establish this strong connection. In general, right, in order for these to actually be connected, 3 things need to be true. We need that it's positive, we need that it's continuous, and we need that it's decreasing. So we're going to write down a statement for kind of each one of these. So I'm going to say that 1 over n plus 1 is positive. And I'm just going to do kind of one sentence to explain why this is the case. So it's positive because n is greater than or equal to 2. So I'm going to say since n is greater than or equal to 2. So notice that our starting point is at n equals 2, and it gets bigger and bigger and bigger and bigger, but you never hit any of the negatives. We don't care about any negative values or things like this. So if we start at 2 and get bigger and bigger and bigger on that domain, right, we're going to have that n plus 1 is going to be positive, right? We have something bigger than 2, and if we add 1 to it, it's going to be, still positive, right? It's going to be 3 or bigger, in fact, but the big thing here is that I care about positive. So I'm going to say it's greater than 0. And so if you take the reciprocal of a positive number, it stays positive. Right? Basically, you can say the n plus 1 is positive, the 1 is positive. So when you take the ratio of those things, that is all positive. All right, 2 more things to check really quick, and then I'll go ahead and take some questions. I see there's more raised hands coming here. So we have positive. Let's talk about continuous. So 1 over n plus 1 is continuous. And a nice way to show that it's continuous is if you plot all of its discontinuities, right? If I can tell you everywhere that it's not continuous, everywhere remaining needs to be continuous. So the only discontinuity here is when n is equal to -1. Remember, for discontinuities, you're looking for division by 0, plugging in like a 0 or a negative number into a natural log, plugging in like plugging in like a negative into a square root. Those are the big cases where you're going to have some discontinuities in a clean function like this. So in particular, right, we have division. So if we divide it by 0, that would be an issue. So it's continuous since, and we'll say that the only discontinuity is at n equals -1. If you plugged in -1, then you'd be divided by 0, and that would be an issue. But so long as you're not plugging in -1, you don't have any other discontinuities. And so in particular, again, we're interested from 2 and bigger. So we're never going to be plugging in -1 into this thing. It's always going to be continuous. So only discontinuity is at n equals -1. So continuous on 2 and bigger. And then finally, the decreasing bit. So 1 over n plus 1 is decreasing since, and again, we could take a derivative of this and say when is the derivative less than 0, which is going to be darn near everywhere here. However, we also came up with those nice theorems, right? And I can say that n plus 1 is increasing. Right? As you plug in larger and larger n's, you get, that this isn't, quite literally, this is a straight line with slope 1 and intercept 1, right? So this is increasing. So if we take the reciprocal of an increasing function, we saw, according to that theorem that we got in the pre-class notes, that this is going to be decreasing. So this right here, these three things establish the link between these two things, the series and the improper integral. Without those three things, you don't have that link. And there are certainly cases, and if you drop any one of these, there are cases where one will converge and one will diverge. And that'll be a problem, right? We want a strong link to say that if one will converge, the other one certainly converges. If one diverges, the other one certainly diverges. And so those three things are what we need to establish that link. Now that we have that link, let me go ahead and quickly just say, right, we can integrate this. This is going to be the natural log of the absolute value of x plus 1. We need to evaluate this from 2 to infinity. Technically, there's a limit right here as t goes to infinity and everything. I think this one's simple enough that maybe we don't need to go through all of the formalities here. And so, right, if I plug in infinity, well, infinity plus 1, a very, very large number plus even more is going to be, you know, towards infinity. As we plug in a larger and larger number into the natural log, this will get larger and larger going off to infinity. Subtracting by a constant isn't going to get you off infinity or not. So this right here is going to go to infinity, aka that it diverges. Since the improper integral diverges, and we know that there is this link, right? We know that whatever the improper integral does, so too does the series, right? So whatever, if it converges, then it converges. If the improper integral diverges, then the series diverges. So since this diverges, we now know with certainty that our original thing diverges. So this series here, 1 over n plus 1, diverges by the integral test. And by the way, if you were kind of guessing with this anyway, and if you said, well, maybe you can't exactly use p series, but maybe it's kind of close enough that maybe we could, notice that your p is equal to 1 here, and at p equals 1, it diverges. So this right here does diverge. Also with the nth term test, right, if you tried to make up, you know, this bad version of the nth term test, which remember I talked about last time, if you just say, hey, the limit of this goes to 0, it converges, right? Here is a case where, no, it doesn't, right? This actually diverges. This actually resembles something close to the harmonic series. Okay, so with this, I'm sure there are questions. Let's go ahead and call on a few folks and then do some Q&A questions as well. Jeff, we haven't heard from you today. What's going on?
Thank you, Professor. If I remember right, earlier in a later chapter, we were told that 0 times infinity is indeterminate.
Yes.
Is that the case for sequences and series as well? Because you mentioned that like multiplying by a constant doesn't change whether it diverges or converges. However, unless the constant is 0, would we have to use like the L'Hopital's rule, and then if that comes up?
Then it really gets into how things are approaching 0 and how things are approaching infinity. If one is just constant at 0 and it's not actually approaching 0, then this is going to be a bit stronger, and it turns out the answer will be 0. But we saw situations where we use the L'Hopital's rule. It's one's approaching 0 and one's approaching infinity, and then the rate of approach really matters, and that's why you use L'Hopital's rule. But if one is fixed at 0, right, and if you're just summing up 0 infinitely many times, right, so if I sum up from n equals 1 to infinity, and my sequence is very, very boring, it's just 0 plus 0 plus 0 plus 0 infinitely many times. Now, formally using our definitions of multiplication, this is 0 times infinity. But because one is not approaching 0, it's just actually 0, this is just going to be equal to 0 here.
Okay, thank you.
Yeah, definitely. It's a very subtle and technical question. So I'm sorry for the subtle and technical answer. All right, Anthony, you have the floor. We haven't heard from you today yet.
Hey, Professor. Is there any instance where we wouldn't be able to use any test?
Yes, certainly. There are some cases where no matter what test you try, it just doesn't happen to work. Admittedly, those don't come up so much in our class on our assessments and whatnot because they don't showcase very well, if you know how to apply the tests. And so, yes, they're certainly out there. If you just like pick out things at random, they certainly do exist, but they're just not going to come up so much because we're going to be interested in seeing if you've learned the content that we've taught in class, and the pre-class videos and all that sort of stuff, and that you can actually apply those.
Thanks, Professor.
Yeah, of course. Let's go ahead and take one Q&A question if we have one, Yuan.
Can you manipulate the 1 over n plus 1 so that there's a clear 1 over n?
Yes. The easiest way to do this, so if you really wanted to make this, like if you wanted to put effort into making this look like a actual P-series situation, this one you can do it because again, it's simple enough. I can make this just a little bit more difficult and then you wouldn't be able to do it. But in this case, right, if we just start writing out these terms, right, so starting at n equals 2, so I'd have 1 over 2 plus 1 is going to be 3. And then 1 over, if I plugged in 3 next, so I'd have 3 plus 1 is 4. Then 1 over, you can guess, probably 5, then 1 over 6, then so on and so forth, right? So you can see that you just take, starting off at n equals 2, you add 1 to that, and then you take the reciprocal. N equals 3, add 1 to that, take the reciprocal, so on and so forth. Now you could instead write this as summing up starting at 3 to infinity, and maybe you'd want to be a little bit more careful, right? Since n is being used down here and starting off at 2, maybe you could use something like m, right? But if you started at m equals 3, then you could just write it as 1 over m here, right? So you'd plug in 1/3, then 1/4, then 1/5, right? And the important thing here is that it's 1 over m raised to the first power. So this will diverge by the P-series test. But this is kind of a very clever thing, right? And again, kind of it works in this case because I chose one that's so simple. In general, you won't be able to pull off a trick like this. So I don't want to, obviously, like this is a lot shorter. So you could say, well, why don't you just teach us that, right? This is something that's very special in this case right here and is not so generalizable. And so that's why learning the integral test and especially, kind of applying to stuff like this will have tremendous value. Good. Okay, let's go ahead and do another problem here. So again, looking at this one, we could go through the list of things, right? We could think about the geometric series test, doesn't work. We could think about the nth term test for divergence, doesn't work. Turns out that the items on the list here do go to 0. We could think about P-series test. You can see here, no matter how you manipulate this one, you're not going to be able to write it as 1 over n to the p. That natural log really throws things off. And so there's no way, even, being very, very clever and whatnot, there's no way to rewrite this as 1 over n to the p. And so the P-series test doesn't work. The only thing that will work is going to be the integral test. So we're going to use the integral test. And again, the first thing that we want to do is establish this strong connection. So we want to make sure that these 3 things, the positive, continuous, and decreasing, actually hold for this function right here. So I'm going to go ahead and say that 1 over n times the natural log of n is positive. And then I have to justify why, right? So I know that, of course, what I'm going to say is that it's made up of lots of positive things, right? So certainly the numerator is positive. And n, right? So n itself, this thing right here is greater than or equal to 2, which is positive, right? It starts at 2, goes 3, 4, 5, right? You never care about any of the negatives. Next up, the natural log. Well, the natural log, let's think about this one for a second. The natural log, it looks like this. It's not exclusively positive, right? But here it hits 0, and then after that, it stays positive, right? Because it's an increasing function here. So it hits 0 here when n is equal to 1, or when x is equal to 1, if we were talking about the natural log of x. So long as you're at 2 or bigger, yeah, it's going to be positive. So the natural log of n is greater than 0 when n is greater than or equal to 2. So long as it's not 1 or smaller than 1, this is going to be positive. And so you have lots of positive pieces, and when you multiply or divide lots of positive things, it stays positive. So this right here is a perfectly fine sentence right here. This is positive since all of the pieces here are positive. We can multiply and divide them and it stays positive. All right, how about continuous? So I'm going to say that this thing is continuous. Natural log of n. And just as before, the way that I'm going to justify that it's continuous is by telling you exactly when it's not continuous, right? So it's not continuous at n equals 0. So notice that n is greater than or equal to 2. So n is not equal to 0. That's a place that we would have a problem, right? And also, if you plugged in 0 or a negative into the natural log, that would be a problem, right? It would not be continuous there. And n is greater than 0. So natural log of n is continuous. So all of the pieces here are continuous, right? We've mapped out all of the discontinuities. You wouldn't want to plug in any negatives. You wouldn't want to plug in 0. But so long as you're not plugging in those things, this makes sense. And you never divide by 0. You never plug in a negative into a natural log or a square root or anything like that. So yes, this is continuous because we know exactly where it's not continuous, and everywhere else it's continuous. And then finally, decreasing. Well, I can say that this is going to be decreasing because n is increasing and the natural log of n is increasing. So of course, if you take the product of these things, we learned in the pre-class videos that this is increasing. And then finally, if you take the reciprocal of an increasing function, it's decreasing. Is decreasing. So again, we kind of look at all of the pieces here. We can say that since our numerator is relatively boring, it's just 1. We're going to put it in terms of a reciprocal function here. And because we have n as an increasing function, remember this just looks like a nice straight line here. The natural log is an increasing function. It looks like this. So when you take the product of them, I don't know what that one looks like, but I can tell you that the product of 2 increasing functions stays increasing, right? And so this right here is going to be decreasing. Again, this maybe Yuan's cringing a little bit. There's some, I'm hand waving a little bit as far as you need it to be positive and increasing. So the fact that we already have positive makes that statement true. Okay, these 3 things establish this strong link, right? That says that instead of considering the series, which again, we're still kind of relatively weak on, we don't know a whole lot about series yet, we can instead consider this improper integral. And we're a lot stronger with integration. So I'm going to go ahead and consider, oops, I should probably write it with x's now. I'm going to instead add up the area under this curve for this continuous function here, 1 over x times the natural log of x. And now I think back to all of my chapter 7 stuff. How do I integrate this one? Right? And it turns out a nice u substitution will do the trick. So if I let u be equal to the natural log of x, notice that du, 1 over x dx, is hanging around this problem, right? So we have this 1 over x dx, right? That's our du very nicely hanging around this problem. So this is going to be equal to the integral of 1 over u du. So again, instead of the natural log, I write u. Instead of the 1 over x dx, I write the du. And so when we integrate this, we're going to have the natural log of the absolute value of u, or the natural log of the absolute value of, and u is equal to the natural log of x. Oof, compositions of the natural log function, never a pretty thing. But we're going to try our best to plug in here from 2 to infinity. And again, I think this one is simple enough that I'm going to try to skip all of the limit stuff sort of deal. And so if I try to plug in infinity here, let's see, we'd have the natural log of the absolute value of the natural log of infinity. Aren't we having fun here? And I'll plug in 2 here. That one's not so bad. But okay, let's just, again, whenever you do a composition, let's evaluate inside out. Tell me in chat, please, what is the natural log of infinity? Or really more appropriately, right, the natural log of larger and larger values approaching infinity. Yes, I agree. Everyone has it so far. It's infinity. So this is going to be the natural log of infinity is infinity, right? And then we take that and we plug it into yet another natural log. Technically, we have to sit there and we have to make it positive. Well, it's already positive. So, right, these absolute values aren't really doing anything. But okay, so we take this infinity and we plug it into yet another natural log. And when you plug it into yet another natural log, well, for the exact same reasons as before, this is still going to be infinite, right? This is still going to approach infinity. And I saw someone bring up that this is a very, very weak infinity. And I agree that it does approach infinity very slowly, but still it does approach infinity. It gets larger and larger and larger. It surpasses any finite number that you choose. And then when you subtract away a little bit off, right, this minus the natural log of the natural log of 2, which by the way, you can plug this into your calculator. It's a little bit weird to write that, but it's a perfectly fine decimal. You can put it into your calculator, right? And so when you subtract away something from infinity, a nice finite number from infinity, that's not going to take you off infinity. It's still going to get larger and larger and larger. And this is going to go off to infinity. And so this right here diverges. And we established with these 3 things up here that there is this link between our improper integral, this thing that we learned from chapter 7, and this new problem that we're trying to solve in today's class in chapter 11, right? And so because we know that this improper integral diverges, we can say that our series diverges. Which, by the way, I'm not sure, maybe with partial credit this would come up a little bit, but I remember with these handwritten exams, this is one thing where folks would get dinked off some points all the time, that they would just say that this right here diverges, and they would just stop writing, But that wasn't the question that was posed to you, right? The question wasn't if the improper integral diverges or not. The question is, does the series diverge or not? And in this case, we know that it does diverge, but this requires one extra sentence, right? So we'll say, so the series that we had here, 1 over n times the natural log of n, starting off at n equals 2 and getting larger, diverges. Why does it diverge? Because of the integral test. And so this right here, is the difference between, if this was like a 12-point question or something like that on an exam, it's either 1 or 2 points taken off. So it was, if you just stop right here, sometimes folks got 10 points, sometimes folks got 11 points, sort of deal, depending on how the grading rubric was made up and all that sort of stuff. But so you do definitely want to think about, you're making a connection, you're coming up with a result for an improper integral, but the last step is always to relate this back to the problem that you had to solve, right? It's kind of like doing the U substitution, right? If you leave your final answer in terms of U's, you're going to get dinked off a point or so because the original problem had X's in it, right? You need to solve the original problem with the original variable, not, this new problem that you've made up with your own U and all that sort of stuff. So it's the same sort of concept here. All right. This one's even more complicated still, so I'm sure there's a few questions. Let's go ahead. Anito, you have the floor here if you have a question for us.
Yeah, so just in general, when we're doing the integral test,
Yeah.
as long as we have the 3 rules and the bounds are right, like for this question, for example, it wouldn't have mattered if n equals 20 to infinity.
Exactly. Yes. And that's where you notice that formally, when we were doing this in the pre-class notes, right, we just said from 1 to infinity.
Yeah.
Right. And it's just because it doesn't look as pretty, and it's just even more confusing if you say a to infinity and you include a's there, right? It just adds this one more layer of complication where technically this is true. You can start at 2 or 3 or 20 or whatever you'd like, right? It just doesn't look as nice, right? So we just give a relatively nice theorem here saying, yeah, 1 to infinity is good. And then, right, I told you in class from last time that you can mess with those bounds a little bit, and that won't really influence whether it's converging or diverging.
All right, for sure. Thank you.
Yeah, no problem. All right, what do we have going on in the Q&A, Yuan?
I think there's someone asking. Maybe a simple one is n can be 1 here, right?
Oh, thank you. Yes, that's a wonderful thing to bring up. I missed one thing in our discontinuity here, right? So I said that it's continuous, and I said that, well, n is greater than or equal to 2, so n itself is not 0. But actually, right, another thing that you would be worried about is if the natural log was equal to 0. And so in this case, we really should say n is greater than 1 here. Excellent point. Because if it was equal to 1, the natural log of 1 would be equal to 0, and you'd be dividing by 0. So yes, thank you very much for that. Good. Let's go ahead. I thought, let's call on one more person who has a hand raised. Jeff, you've got the floor if you have another question for us.
Yes, I do. Just a quick one. Is there any pitfalls to just, if you're able to look at it and determine whether the denominator increases quicker than the numerator, and saying, well, if that happens, it converges?
So the question was, are there any pitfalls to being able to determine this?
Well, I know that for the partial credit, you need to specify why, but to make sure that you're going down the right track, you say the denominator is increasing quicker than the numerator, that means it's going to converge.
Yeah, you just have to be careful, I suppose, about what do you mean by quicker? Because, like, for instance, if you say, if you compare like n squared versus like 2n squared, right? 2n squared does increase quicker, but it's not more quicker enough.
Right.
That was
I don't mean by that because that's to the same degree. I mean, looking at the degrees.
Exactly. So if you look at n squared versus n cubed, now this is quicker enough, right?
Right.
So yeah, that would be my main concern about coming up with a theorem like this, right? And that would be a main pitfall. You have to know exactly what you mean by when the denominator increases more quickly than the numerator, right? And exactly what are the caveats to that.
Okay. Yeah, because when I look at it, it's the same kind of rules as when we determined, I don't remember what section it was, but basically if you had the same powers, it increased at the same rate, and then you just took the constants.
Yeah. Yeah, with horizontal asymptotes, there is a strong connection with this. I agree.
Okay, thank you.
Yeah, definitely. All right, so let's go ahead and peek at this one here, determine whether this is a convergent series. So again, going down the list, it turns out that you can't use the nth term test for divergence. You can't use the geometric series test. You can't use p-series test. So right now, all we know is the integral test. So for the integral test, we're going to go through and we're going to make this strong connection. So the first thing is 4 divided by n squared plus 1 is positive. Since all of the pieces are positive, right? So since 4 is greater than 0, it's positive, and n squared plus 1 is greater than 0. Well, even all the time, right? But in particular, when n is 1 and larger, this will certainly be true. So when you take the two positives and you divide them, it stays positive. 4 over n squared plus 1 is continuous. And the reason why it's continuous, well, in order to divide by 0 here, you'd have to have an imaginary number, right? And so this is really that n squared plus 1 is not equal to 0 for any real number. So actually it's continuous everywhere. And in particular on the interval that we're interested in, from 1 and larger, it's continuous. And then finally, it's decreasing. And I'm going to go ahead, and I see that we're basically out of time. So, I mean, it's for the same reasons that we did before. This is essentially a reciprocal. We've multiplied by a constant of 4 here, and n squared plus 1 is an increasing function when n is 1 and larger. So I'll write this before I post it online here later. But I wanted to get to, if you take the integral here of now this thing that we've made this strong connection with, And again, we're integrating from 1 to infinity, looking at the bounds here for our series. That's gives us our bounds for improper integral. Someone remind me, how do I integrate this? How do I integrate 4 over x squared plus 1? Yep, so this is going to be an arctangent. So this is 4 times arctangent of x. So this is, again, kind of when you come to actually integrating these things, you basically have the potential for any type of integral, right? We talked about back here, this was a simple u substitution. Here's one from chapter 6, right? Where you could have one of these inverse trig functions, in particular inverse tangent here. And now if we were to evaluate this from 1 to infinity, we'd have tangent inverse of infinity minus tangent inverse of 1. I'm here to say that tangent inverse of 1 is going to be pi over 4. You can double check. If you plug in pi over 4 into tangent, it will output 1. Now, how about tangent inverse of infinity? This is one that sometimes is a little bit tricky, right? So, yeah, so this is one where it's not infinity. Folks who are speaking up in chat have it right that it's pi over 2. And this has come up a couple times in class so far, what tangent inverse looks like. But remember, this has horizontal asymptotes. As you go off to infinity, it approaches pi over 2, and it goes off towards negative infinity, it approaches negative pi over 2. So this right here, the answer is pi. So now this converges, right? Because this actually goes to some finite real number, right? But again, you wouldn't want to just stop here. You need to conclude this with, how does this relate to the problem that was posed to us? We had a series here. We talked about an improper integral. So I'm going to say, so because we made this strong connection from n equals 1 to infinity of our original series here, that this converges. By the way, another place where sometimes folks get points marked off is they go on and they say that it converges to pi. No, it doesn't. The improper integral converges to pi. The series converges to something else. And we don't really know just by looking at this here what it converges to, but it's not pi, right? The areas are going to be different. So, but we can say that it converges by the integral test. But we can't say necessarily what it converges to. So again, we're only asking, does it converge or not? Not so much what it converges to, because in general, that's a very difficult question and one that I'm going to what's the word that I'm looking for? Bore you with in Friday before class, maybe. So we'll go into what it takes in order to show something like this, what it converges to actually. It's very, very difficult. All right. Thank you guys for sticking it out with me. I see that we're well over time, so this is where we're going to end. I'll go ahead and stop recording.